Good morning, everyone. My name is Ahmad Rashed, and I am a master's student at American University of Sharjah. I am studying under the supervision of Dr. Rami Hawileh and Jamal Abdalla, and working with Haya Mhanna, who is also one of the authors in this study. The title of the study is The Performance of RC Beams Externally Strengthened with Hybrid CFRP and PET-FRP Laminates. This is the outline of today's presentation. I will start with brief introduction, then research significance, moving on to explaining the experimental program and result discussion. Finally, I will conclude with the conclusion. Fiber reinforced polymer materials are being extensively used on the construction industry to retrofit existing RC structures. In fact, due to its non-corrosive nature, FRPs has been replacing traditional strengthening methods that can be corrode, such as steel plates. There are several advantages of FRPs, such as high strength-to-weight ratio, high durability, and it is introducing fast and economical rehabilitation on maintaining different RC structures. On the other hand, the main disadvantages are debonding and delamination. The enhancement in flexure capacity of RC beams can be achieved by bonding the FRP laminates along the longitudinal direction of the fibers on the tension side of the beam's cross-section. The conventional FRP composite sheets used in the construction industry are carbon FRP, glass FRP, aramid FRP, and basalt FRP. These conventional materials are linear elastic materials when loaded in tension and rupture in a brittle manner at low strain. Recently, a new type of FRP material composed such as spin, PET, and BAF fibers have been developed to encounter the drawbacks of conventional FRPs. Compared to conventional FRPs, PET-FRP has large deformability with a rupture strain exceeds 7% and poses a nonlinear stress-strain relationship. Another key advantage of PET-FRP is providing a solution that encourages an environmentally friendly concept of sustainability and cost-effective material since it's manufactured from recycled scrap polymer products. Using PET-FRP in the retrofitting industry reduce construction waste and enhance the capacity of structure. However, these types of FRPs has lower stiffness and tensile strength than conventional FRPs, which could be compensated by using more FRP layers. Their significance. The elastic and brittle nature of conventional FRPs causes significant reduction in the ductility of strengthened beam, which result in unfavorable and sudden brittle failure mode without any warning signs. In order to enhance beam strength, several research studies proposed hybrid strengthening systems by stacking high stiffness and strength CFRP sheets with lower stiffness sheets, such as GFRP or PFRP, to the soffit of RC beams via epoxy adhesives. Such hybrid systems improve the mechanical properties of the strengthening composite laminate that enhance both the flexure strength and ductility of RC beam specimens. However, all these conventional FRPs rupture at low strain levels from 1.5 to 3%, which limit the beam's ductility enhancement. All studies investigating hybrid combinations of FRPs have involved conventional FRPs with linear stress-strain behavior. Thus far, there are no studies conducted on RC beams to investigate the hybrid effect of combining high-strength conventional CFRP with PET-FRP sheets that has a bilinear stress-strain relationship and significantly higher rupture strain that exceeds 7%. The main aim of this study is to propose a new hybrid and ductile strengthening composite system to externally strengthen RC beams in flexure by bonding CFRP with PET-FRP sheets to the beam soffit in different combinations via epoxy adhesives. Moving to the experimental program. The experimental program in this research was divided into two stages, which they are co-bond tensile tests for all the strengthening schemes and flexural tests for all the beams. A total of 5 beams with a length of 1840 mm, a depth of 240 mm, and a width of 125 mm. The effective depth of the specimens is 205 mm. Specimens was reinforced in flexure with 2 number 10 bars in tension zone and 2 number 8 bars in compression zone. In addition, it was reinforced in shear with number 10 stirrups spaced at 100 mm center to center. The flexure strengthening laminate had a total length of 1640 mm and width of 125 mm. The beams test matrix of the study is shown in this table. The beams have some variations such as type of FRP since CFRP and PET-FRP were used, number of FRP layers, and stacking sequence. The first beam was tested as a control specimen. Two beams were strengthened with one layer of CFRP and PET-FRP. Finally, the last two beams were strengthened with two layers of both strengthening materials with different consequences. Moving on to material properties, the average concrete strength of cubes was recorded to be 46.31 megapascal and the cylindrical compressive strength was 38.44 megapascal. Steel properties were recorded by applying a tensile test, then they were listed in the table below. In order to examine the mechanical properties of FRP laminates and its hybrid mix, each FRP laminate configuration was repeated 3 times to ensure accurate and consistent results. The compounds were prepared using the wet layup process, cut using a milling machine for a dimension of 200 mm by 15 mm, and then test them in tension. As shown in this graph, C samples had a linear elastic reaction and B sample had a bilinear stress-strain relationship with two moduluses. On the other hand, hybrid flat compounds behaved in a linear elastic manner before failing at low rupture strain, which is slightly higher than that on CFRP sheet. This shows that the failure of the hybrid mix was dominated by the failure of the CFRP sheets. All beams were tested under 4-point bending at a displacement controlled mode rate of 2 mm per minute and shear span of 600 mm. LVDT was placed under the beam's midspan to capture the deflection of the beams. Moreover, strain in the concrete and steel were monitored by placing strain gauges at midspan on the top of the concrete and on the toe bottom of steel reinforcement bars. Moving on to results and discussion. The results that were observed from the flexural test are shown in this table. It was clear that the ultimate load capacity of all strengthened specimens increased significantly compared to the control beam specimen. The highest ultimate load was observed by strengthening the RC beams with CP strengthening sheets. However, these multiple layers reduce the ductility significantly. It can be noticed that the PE beam slightly increased both flexural strength and ductility compared to the control specimen. The failure mode of all the beams changed from steel yielding and concrete crushing to debonding of the concrete cover and debonding of FRP sheets. As shown in these figures, the failure mode of C, PC, and CB beams was the bonding of the concrete cover, which initiated by shear cracks along with lower steel reinforcement and ended up with the lamination of concrete cover. The failure mode of the BMP was the bonding of FRP and concrete crushing initiated by propagation of intermediate cracks, which result in the lamination of the FRP sheet. As a result, none of the strengthening schemes reached to its optimum capacity since no fracture in FRB was witnessed. In this load deflection curve, it clearly indicates that the ultimate load carrying capacity of the strengthened specimen outweighed the control beam, particularly the enhancement in the yield and ultimate load compared to CP. Specimen C, CP, and PC provided similar strength improvement, while specimen P displayed inferior capacity than CFRP strengthening beams. This is due to the significantly higher tensile capacity of CFRP compared to PET-FRP laminates, which resulted in better performance in terms of load carrying capacity. However, the strength enhancement was at the expense of ductility, where the deflection at ultimate and failure of specimen C, CB, and PC was reduced compared to the control beam. An unusual behavior was observed in specimen P, where the deflection at yield, ultimate, and failure loads was enhanced. Consequently, the ductility at ultimate and failure of specimen P outweighed CP. This interesting performance is untypical for FRB strengthening beams, and it is a result of large rupture strain capacity of the PET fibers. Here is another comparison graph that shows improvement with respect to control specimen. The load carrying capacity improvement of C-beam was recorded to be enhanced by 47%. On the other hand, the ductility at ultimate and failure of B-beam enhanced up to 3 and 9%. Beam BC and CP showed similar percentage increase in flexure capacity that reached up to 46 and 48% and decreased in ductility by 66%. Finally, the conclusion. The ultimate load carrying capacity of the strengthened specimen outwitted the control beam by 24 to 48%. The load carrying capacity of all the beams that consist of CFRP laminate was superior to that of the PET strengthened beam. However, the strength enhancement was at the expense of the ductility, which was reduced by 50 to 66% at failure load compared to the control beam. The PET strengthened beam displayed an outstanding ductility behavior up to 9% enhancement than that in the control beam. The stiffness of the specimen strengthened with the hybrid mix of CFRP and PET-FRP laminates surpassed that of single sheet of CFRP and PET-FRP. However, the strength and deformation capacity of the hybrid mix was limited by low strain capacity of the CFRP laminate. Therefore, it is recommended to anchor the laminates to exploit the benefits of both types of FRPs. Thank you for your attention.